So we're continuing the method of partial fractions. This is part 7. Now it's a lot more stuff around here. Oops, sorry. Um, so this one, the numerator is of degree 4, and denominator is of degree 2 times 2, 4 plus 1, 5. So the step 1 is already done. That's good. Step 2, I see that the denominator has linear and quadratic with only roots that are non-real. And so 2 is done. So how do I set this up? Here's how. So the fraction is going to be, which is x to the 4th plus x to the 3 plus 3x squared plus 2x plus 3 over this is going to be equal to x plus 1. That's the partial fraction over x plus 1, which is the numerator has to be a constant. Then x squared plus 1, the numerator has to be of linear format. Then the dx plus e over x squared plus 1 to power 2, basically. Now do the common denominator again. We want this left hand side to be equal to the sum of all those partial fractions. Therefore I have to do the common denominator, and so on and so forth. So for the right hand side, what do I get? I get the denominator is going to be x plus 1 times x squared plus 1, which you have figured it out. It's the common denominator is exactly where you started with, and that's not uncommon. That's what's going to happen. That's a routine. In here, what did I multiply denominator of the first one? I multiplied it by x squared plus 1 to power 2. So the numerator has to be done like that too. What I do to the fraction 2, I multiply the denominator by x plus 1 and x squared plus 1. So I write it as plus bx plus c times x plus 1 times x squared plus 1. And then the last one, what I changed in the last fraction, I multiply the denominator by x plus 1 plus dx plus e times x plus 1. And then now we're at this point that the numerators should be set equal to each other, except the numerator is somewhat of a mess up here. Basically, there are ways of basically solving some of these coefficients without completely expanding everything out, and those ways are nicer and work nicely basically for us. One way is that, so what is the plan? What is the step 3 again? So far you haven't had anything that turned out to be this complex. So the step 3 is without expanding everything. Now I'm just going to look at this. It is a long one, isn't it? So plus bx plus c times x plus 1 times times x squared plus 1 plus dx plus e times x plus 1. So basically, one of the ways of resolving this thing is to start with whatever coefficient you know what it is, you know how to find using other methods, and then find the other coefficient using solving systems of equations, basically. In this specific case, I can tell that on the right hand side, I will get basically a coefficient of x to the fourth is going to be a. A plus the coefficient of x to the fourth is going to be a plus b. And so that's one piece of knowledge that I have, and that is nice knowledge to have. But I also can actually find a without expanding this at all. And how do I find a? If this equation holds, right, then it should hold for x equal to -1. And where did I get the -1? -1 comes from the root of x plus 1. Okay, so if the equation holds, then it should be okay for also the root of and for the root -1. So how does that work? If I plug in x equal to -1 on the right hand side, I get -1 to power 1, which is to power 4, which is 1, plus -1 to power 3, which is -1. 1, -1, plus 3, minus 2, plus 3. And so here I get 4 on the, by plugging x equal to -1, I get 4 on this side, and on this side these two terms will be 0, and -1 to power 2 is 1 plus 1 to power 2, 4. I get 4a on the right side. So I can also solve that a is equal to 1, because 4 equal to 4a, a equal to 1, without doing anything extra. Then I can easily also see that the coefficient of x to the fourth, look at this. This term does not have x to the power 4. This term has x to the power 4, and that would be by multiplication of the first term of each factor, and that coefficient is going to be b. That one has x to the power 4, and that again comes from multiplication of basically each multiplication of x squared by x squared, which is 1. So let's write this again. From here I know a is equal to 1. Now from all this discussion is that I know that the coefficient of x to the power 4 is equal to a plus b on the right. Is a plus b, coefficient on the left is equal to 1, a was equal to 1, so b is equal to 0, basically. So I figured out this one is equal to 0. That simplified things a little bit, didn't it? Now, what else can I figure out of this? I know that that a constant 1 appears in here, and a constant c appears in here, and a constant e appears in here. So constant on the left side is 3, and what I have here is 1 plus c plus e. So 3 is equal to 1 plus c plus e. and therefore c plus e is equal to 2. So I got an equation. I couldn't quite solve for that. Let's see if I can find anything involving d. D is, let's see, d gives you the coefficient for x squared in here. Over here, the coefficient for x squared is going to be, what is the coefficient for x squared? You will have basically, when you multiply this through, the coefficient for x squared is going to be c, and over here coefficient for x squared is 2. So on the left hand side is 3. So again, 3 is equal to, I said 2 over there, plus in here we will get a c, and plus in here we get a d. So this gives me that c plus d is equal to 1. And so far, how many things we have found and what we have not tried? We have not tried x to the power 3. Where do we get x to the power 3? X to the power 3 comes from right here again. C is the coefficient for x to the power 3. Over here you don't have any x to the power 3, so c should be equal to, so 1 should be equal to c, and that gives you, out of these two, it gives you e is equal to 1, and d is equal to 0. So we solved them all that way. So I found a is equal to 1, b is equal to 0, c is equal to 1, d is equal to 0, and e is equal to 1. Okay. So now I can take the antiderivative and solve it. So what I wanted to show you is that I didn't have to write down all the basically equations to solve for a, b, and c, and d. And there were a little bit of a shortcuts. And the reason I did that was that this is a very, very long partial fraction to just go with the regular methods. And so the last part, and I'm going to erase this, the last part is to use the partial fractions the partial fractions that you found and find the antiderivative. Okay, back to taking the antiderivative. And in here, so the antiderivative is going to be equal to 1 over x plus integral of 1 over x plus 1 plus integral of 1 over x squared plus 1 dx plus integral of 1 over x squared plus 1 to power 2 dx. And the first one of the integrals, I know that's natural log of ln of x. The second one I know is the arctan of x. And then the third one, I have to do the the substitution, the trig substitution, to find the answer. And that would be, so if I set x equal to tan of theta, then I get dx equal to secant squared theta d theta. And then by replacing those, I will get in the bottom, I would get 1 plus tan squared theta to power 2 and secant squared theta d theta. Reminder that secant squared theta is actually equal to 1 plus tangent squared theta. So replacing that by that values, I get secant to the 4th of theta d theta. Simplify, and that ends up to be secant squared is 1 over secant squared and secant to the 4th of theta are going to simplify, and then what I get is reciprocal of secant squared is going to be cosine squared theta d theta, which is the integral of, using the trig substitution, trig identity, I get 1 plus cosine 2 theta divided by 2 d theta, and that is basically theta half plus sine 2 theta divided by 2 plus c. And now sine 2 theta is equal to, so theta half plus 2 sine theta cosine theta divided by 2 plus c. So sine theta cosine theta. Now using the theta half is going to be just arc tangent half arc tangent x divided by half, right? But this part, theta is an angle such that its tangent is x. Therefore, by Pythagorean theorem, the sine is going to be, sine of theta is going to be x over x squared plus 1, and the cosine theta is going to be 1 over x squared plus 1. So this part of the answer is going to be x over x squared plus 1 plus c. That was the work done just for the last integral. And so this thing can get really, really quickly, really, really big. Have some methods of putting it in perspective and how to solve it. And in reality, when you're really using these in real life problems, and a lot of times even in differential equations and in circuits, you're not directly taking the integrals, but you're using the method of partial fractions in one way or another. And it gets really, really big, really, really quick. So this part is going to be in common with this problem and those in those courses also. And so have some method of simplifying things and figuring things out. That's what I'm trying to promote at this point.